Hello, I'm Brad Jewell and my project is VI Precision. The objective of my project was to create a device that could precisely measure where a durable target was hit by a projectile. So, how did it turn out? We'll get to that, but first let me step you through some of the learnings of this project. The initial concept for this project was to allow a competitive target shooter to practice distance shooting without requiring them to go downrange or use a spotting scope to identify points of impact. I also believe this data could be used in a form of replay that would allow the user to share their session data with their coach or club members at a later time. For my market research, I investigated existing options and found there are several companies that make products that do this today, but the cheapest option was $800, with the rest exceeding $3,000. Most of the existing products also relied on local ad hoc networking, which requires additional hardware components. In addition to product research, I looked into estimates on the number of competitive target shooters and small arms owners in the United States. I found that as of 2017, there are an estimated 30 million individuals competing in target shooting competitions in the United States. I also found that there are close to 400 million civilian owned firearms in the United States as of 2018. I believe this provides enough indication that there may be a market for an IoT based target to continue to the proof of concept phase. My research had indicated that it was possible to take piezoelectric elements to create sensors that could be used to provide the necessary data for multilateration. With that, I could determine and illustrate where the point of impact occurred. When I first started this project, I acquired a number of piezo elements from Amazon, and I thought I'd start testing. The first issue I ran into was these elements can create quite a bit of voltage without a lot of stimulus. Just flicking the sensor could easily read over 5 volts. With a little more research, I came across a blog post from DefProc Engineering. The post described how two Schottky diodes work together to rectify the signal, removing the negative voltage dips. The Zener diode allows voltage over 3.3 volts to drain off to ground, protecting my circuit from excessive voltage. The resistor and capacitor work as a timing circuit to smooth out the voltage, giving me more time to read the value off the sensor. At this point, I was starting to think this was going to be too simple. That feeling did not last long. The next thing I ran into was that my piezo elements were fragile. I tried a number of options to make them more durable, but these options prevented the piezo material from flexing, which is what generates the voltage. Plastidip provided protection and didn't appear to reduce the voltage below my operating threshold. At this point, I put together two sample circuits with breadboards and began testing with the argon. During my initial tests, I used polling and attempted to pull the sensors as quickly as possible, with no delay in the loop. These tests showed that my timestamps between reading the two sensors was consistently around 59 microseconds. For my long-term plans with this project, that would not be fast enough to read a shockwave traveling through steel. Shockwaves through steel travel at approximately 5.96 millimeters per microsecond. Knowing I wanted to invest in this project long term, I went out and I bought an oscilloscope so I could really understand my circuit. The oscilloscope turned out to be both a curse and a blessing for this project. In reality, it would have been incredibly difficult to make as much progress as I have without it, but I also stumbled through misusing and misinterpreting the device. In these first images, I hadn't even taken the time to learn how to grab a basic screenshot from the device itself. Not taking the time to learn my new tools was a critical mistake. By taking the argon out of my testing and connecting my scope to the circuit directly, I was now able to visualize the exact results of my sensor readings. This was really exciting as I could see the general concept was working. When I tapped on my target, the sensor that was closer to the tap showed voltage before the sensor that was further away. However, I didn't notice it at the time, but if you look closely in this image, you'll see the yellow line, channel 1, has the voltage division set to 2 volts, and the blue line, channel 2, is set to 500 millivolts. I spent countless hours trying to determine why the second channel was less sensitive than the first. I built and rebuilt the circuits, I tried a variety of tests before I gave up and decided I would only work with channel 1. When I thought my circuit was working, I tried it with the argon, and my results were lackluster at best. After losing a number of additional hours to various tests, I ended up removing my piezo elements from the equation, and I attempted to use momentary switches to prove out my concept. When they worked as expected, I started looking for a way to create a type of momentary switch out of the signal from my piezo circuit. More research led me to something called a MOSFET transistor. The name triggered a memory, and I went back to the DefProc post, and I found they had made a second version of their circuit using a FET. Sure enough, they were using an NPN MOSFET transistor. The NPN MOSFET effectively acts as a pull-up momentary switch. When the voltage is applied to the gate of the transistor, the switch engages, creating a low reading. This value can be used to trigger interrupts on the argon. The next day, I rush over to Micro Center and I pick up the one style of NPN MOSFET they had in stock. Thankfully, its specs made it look like it would fit my use well, and I thought I was in great shape. Unfortunately, when I tried putting it in my design, it just wasn't working. I just could not get the results that I was expecting. After realizing it wasn't going to work, I gave up and I ordered the exact part number DefProc used in their build. It was a surface mount component, so I had to order some breakout boards and learn to improve my lackluster soldering abilities. When I received the new parts and had my new circuit built, I still wasn't getting the results I expected. At this point, I needed additional help, so I called my older brother. My brother has an academic background in computer engineering and knows a few friends that still work in the trade actively. After spending the weekend FaceTiming through the problem, I learned several things. First, don't call a computer engineer or electrical engineer without having a schematic and data sheets handy. Second, building and debugging a circuit is remarkably similar to writing software. Solder and pray works about as well as code and pray. Build and test deliberately. Third, RTFM still rules the day. Channel 1 on my oscilloscope was multiplying the input by 10 times. This meant the voltage from the piezo element was not nearly as high as I had been expecting. This also meant that the voltage from my pull-up signal on the MOSFET was incorrect. The resistor I had used may have worked for a 5-volt Arduino, but in my circuits, the pull-up value was registering as 1.7 volts rather than 3.3. This resulted in my interrupts firing erratically. With my test circuits working and having learned more about the settings in my scope, I was finally ready to work with my target. I wanted to be able to positively identify where I was hitting on my target and compare it to the results I was posting to the server. I took a 2-foot by 2-foot piece of plywood and marked out a grid of 1-inch increments. I then placed the sensors on 4 corners of the back of the plywood. Now I could use a Nerf gun to shoot the specific marked regions of the target to test consistency. At this point in the project, I'm attempting to use simple subtraction between the timestamps of each of the sensors to determine if the time difference is repeatable for the impact point. With the sensors on the far outside corners, I was unable to achieve regular consistency in the time difference between sensors. After a little bit of research, I speculated that these readings may have resulted from the way the shock wave behaved when it reached the outside edge of the target. This simple test using food coloring and water illustrates what I believe is happening. As the wave expands in concentric rings, it redirects back on itself when the outer ring starts to impact the edge. For my next round of testing, I moved the sensors inward by 3 inches in each direction. My theory was that this would allow the wave to pass over the sensors before echoing off the edges. Testing with the new sensor location initially showed consistent results, but they still weren't exactly what I was expecting. While the results were reproducible, the time differences between each pair of sensors did not seem to be consistent based on the distance between each sensor. I'd expected if it took 1 millisecond for the shockwave to travel between the top left and top right sensor, it would take roughly the same amount of time between the bottom left and bottom right sensor. This was not the case. I went back to testing with my scope and I found that if I moved particular sensors to different positions on the target, the time delay would follow those sensors. Because I was able to create a reproducible impact of force and location, this led me to believe my sensor was the variable that was changing. To test this, I created a weighted pendulum out of a paint stick and some nuts and bolts. Then I marked off the angle that the paint stick would trigger each of my sensors. What I found was some of my sensors were less sensitive than others. After creating new sensors and testing that each one was triggering at the same angle, I was able to continue testing. But after a few more rounds of testing, I found that an additional sensor was losing sensitivity. At this point, I identified that this is an area of my project that needs more research. Given the short time before the final presentation, I decided to note the concern and set up my testing with 4 new piezo elements. The last physical challenge I ran into on this build was the material of the target. I started testing with plywood and ran into challenges of my sensors not always triggering and the time differences between the pairs of sensors not correlating with the distance between the sensors. When I switched my target backing to cardboard, I found that my sensors were reliably triggered, but the time it took for the vibration to travel vertically was much less than it was horizontally. I believe this was related to the hollow vertical channels of the cardboard. My final material was a piece of sheet metal that I took off an old grill. After cutting off the angled sides of the material, the sheet became a uniform piece of homogeneous material. This made the resonance of the target consistent in each direction. My final changes to the target came from suspending the target from all 4 corners rather than just the top corners. In addition, I used compression springs to help balance the tension between the 4 corners. All right, well, let's take a look at the results and see what happened. So here we've got my son is shooting with his Nerf gun, and in the upper right hand corner I'm showing the Excel spreadsheet that we used from our temperature demo. So you can see as he's hitting the target, I'm feeding in my sensor timings from the Argon, and that gives you just a simple example. So I'm just using really basic subtraction to get the time differences to plot it out. This is not the full trilateration, but that's a pretty reasonable result. I take a few shots at it. It's not that bad. They're pretty close. Not quite the precision that I'm looking for, but I'm also not using true trilateration, let alone multilateration. And here you can see the windage 2, elevation 2. Those are malfunctions in my sensor. I'm still having some challenges with that. Here's an example of an even lower speed projectile hitting the target, and it's triggering the results. Using an airsoft gun, that's about 230 feet per second. That's faster target, and it's triggering great. Right here, I'm showing this is my control process. So I can hit the exact same target, exact same spot, basically point blank, trigger it 4 or 5 times, go around on each of the corners, and then hit it in the center a few times. And this is really my results. This is my value of this project. Check out that center cluster. I've got 5 hits, or 4 hits in this case, basically right on top of each other. I've got them in the top left and the bottom left. My bottom right sensor is malfunctioning. That's causing me some grief. But the concept works. There's just more to work on. I may have run out of time on this project, but I'm really proud of what I accomplished. I'd had to go through a number of prototypes. I built out a lot of things to test, and I show promising results. I even got to the point where I added in Calm Tech to help me do the debugging. I had challenges with seeing when all the sensors were registering, and it got tiring to go back to the computer every time to see if the event fired. So I created a little tune, added a piezoelectric buzzer, and now I have sounds to tell me whether some of the sensors fired or all the sensors fired. I have a toggle switch to turn sound on and off, and I have a toggle switch to alter it to mode for calibration mode, which I did not get to. But I still had one burning desire left. What would happen if I put this to use with a firearm? What would happen with a 22 caliber rifle or a 45 pistol? I just had to find out, so I threw one more test at this. I think you're going to like it. I taped my project to a sawhorse behind the suspended steel plate, and we shot it with a 22 and a 45. This gives us a great reference of a small caliber, low impact firearm as well as a large caliber, high impact firearm. I used a hammer on the steel plate to mark my control, and you can see that each of the lines on the grid indicate about a 1 inch reference. So I was a little off on the center point, but when you look at the end results between the 22 and the 45, these lined up pretty darn well to the scarring. This is still using just simple subtraction for placement. I am hoping to follow through with the trilateration in the near future. Thanks for watching. This has been VI Precision, and I'm happy to answer any questions. Thank you.